In the last video, we learned what it meant to take the product of two matrices. So if we have one matrix A, and it's an m by n matrix, and then we have some other matrix B, let's say that's an n by k matrix, then we've defined the product of A and B, so A and B, the product of A and B, to be equal to. And actually, before I define the product, let me just write B out as just a collection of column vectors. So we know that B can be written as a column vector B1, another column vector B2, and all the way it's going to have k of them because it has exactly k columns. So BK. So in the last video, we defined the product of A and B, and they have to have the columns of A have to be the same as the rows of B in order for this to be well defined. But we define this product to be equal to A times each of the column vectors of B. So it's equal to, let me switch back to that color. It's equal to A times, let me do it in the color that I did it, A times B1. And then the second column of our product is going to be A times B2, A times B2. Our third product is going to be A times B3, B3, all the way to A times BK. A times BK, BK, right there. And the whole motivation for this, you've probably seen this before, maybe in your Algebra 2 class. It might have not been defined exactly this way, but this is equivalent to what you probably saw in your Algebra 2 class. But the neat thing about this definition is that the motivation came from the composition of two linear transformations whose transformation matrices were the matrices A and B, and I showed you that in the last video. But with that said, let's actually compute some matrix-matrix products just so you get the hang of it. So let's say that I have the matrix A. Let's say that A is equal to the matrix 1, minus 1, 2, 0, minus 2, and 1. I keep the numbers low to keep our arithmetic fairly straightforward. And let's say that I have the matrix B, and let's say that it is equal to 1, 0, 1, 1, 2, 0, 1, minus 1, and then 3, 1, 0, 2. So A is a 2 by 3 matrix. It's 2 by 3, 2 rows, 3 columns, and B is a 3 by 4 matrix. So by our definition, what is the product AB going to be equal to? Well, we know it's well defined because the number of columns here is equal to the number of rows. So we can actually take these matrix vector products. You'll see that in a second. So AB is equal to the matrix A times the column vector 1, 2, 3. That's going to be the first column in our product matrix. Then the second one is going to be the matrix A times the column 0, 0, 1. The third column is going to be the matrix A times the column vector 1, 1, 0. And then the fourth column in our product vector is going to be the matrix A times the column vector 1, minus 1, 2. And this, when we write it like this, it should be clear why this has to be, why the number of columns in A have to be the number of rows in B. Because the column vectors in B are going to have the same number of components as the number of rows in B. So all of the column vectors in B, so if we call this B1, B2, B3, B4, all of my BI's, let me write it this way. All of my BI's, where this I could be 1, 2, or 3, or 4, are all members of R3. So we only have matrix vector products well defined when the number of columns in your matrix are equivalent to essentially the dimensionality of your vectors. That's why that number and that number has to be the same. Well, now we've reduced our matrix-matrix product problem to just 4 different matrix vector product problems, so we can just multiply these. This is nothing new to us. So let's do it. Let's do it. And so what is this equal to? So AB, let me rewrite it. AB, my product vector, is going to be equal to, so this first column is the matrix A times the column vector 1, 2, 3. And how did we define that? Remember, one way to think about it is that this is equal to you can kind of think of it as each of the rows of A dotted with the column here of B. Or even better, this is the transpose of some matrix, right? Like let me write this way. If A is equal to, the transpose of some vector. Let's say that A is equal to the column vector 0, -1, 2. Then A transpose, and I haven't talked about transposes a lot yet, but I think you get the idea. You just change all of the columns into rows. So A transpose will just be equal to 0, -1, 2. You just go from a column vector to a row vector. So if we call this thing here A transpose, then when we take the product of our matrix A times this vector, we essentially are just taking we're just taking A and dotting with this guy for our first row in our first column. So let me do it that way. So I'm going to write it in that notation. So this is going to be the matrix, or the vector 1, -1, 2. That's essentially that row right there represented as a column dotted with 1, 2, 3. Actually, let me do it in that color, just so I can later switch to one color to make things simple. But dotted with 1, 2, 3. So we just took that row, or I guess the column equivalent of that row, and dotted with this. And I wrote it like this because we've only defined dot products for column vectors. I could do it maybe for row vectors, but no need to make a new definition. And then the next, so that's going to be the first entry in this matrix vector product. The second entry is going to be the second row of A. The second row of A essentially dotted with this vector right there. So it's going to be equal to 0, -2, and 1 dotted with 1, 2, 3. Dotted with 1, 2, 3. And we just keep doing that. And I'll just switch maybe to one neutral color now. So then A times 0, 0, 1, that's going to be the first row of A, expressed as a column vector. So we can write it like this. 1, -1, 2, dot